How are you today? Our topic today is halogen exchange reactions. The SN2 reaction provides a useful method for synthesizing alkyl iodides and fluorides, which are more difficult to make than alkyl chlorides and alkyl bromides, as you've seen in our earlier lectures, where you could easily synthesize alkyl chlorides and bromides, beginning with alcohols and reacting with different reagents, or even using the free radical halogenation process. But it is harder to synthesize alkyl iodide and alkyl fluorides, and one of the ways in which this can be synthesized is through halogen exchange reactions. Halides can be converted to other halides by halogen exchange reactions in which one halide displaces another. Iodide is a good nucleophile, and many alkyl chlorides react with sodium iodide to give alkyl iodides. Alkyl fluorides are difficult to synthesize directly, and they are often made by treating alkyl chlorides and alkyl bromides with potassium fluoride under conditions that use a crown ether and an aprotic solvent to enhance the normally weak nucleophilicity of the fluoride ion. So this is a general reaction on how halogen exchange reactions take place to synthesize alkyl iodides and also alkyl fluorides, which are harder to synthesize as compared to the alkyl chlorides and alkyl bromides. So you have this as the alkyl chloride or alkyl bromide as the substrate, react with the iodide as the nucleophile, and of course the bromide or the chloride will be displaced with the iodide ion to form the alkyl iodide. Similarly, if you start with an alkyl bromide or alkyl chloride, react with potassium fluoride, which is a source of the fluoride ions. And the fluoride ions, of course, will be the nucleophiles, electron-rich species, which are going to donate them to the electrophilic carbon, which is attached to the chlorine or bromine atom to form the alkyl fluoride plus the potassium chloride or potassium bromide, depending on the substrate which was used to synthesize this particular compound. So these are specific examples where you are beginning with an allyl chloride reacting with sodium iodide to form an allyl iodide plus sodium chloride. So of course, this is a primary alkyl chloride, because this carbon which is bearing the chlorine atom or bonded to the chlorine atom is sp3 hybridized, although in the chain it also has a double bond. But when you consider classifying these halogenated hydrocarbons, it means you look at the carbon which is bearing the halogen. Is it sp3 hybridized, or is it sp2 hybridized and is of the double bond, or sp2 hybridized of an aromatic ring? So this is sp3 hybridized and it's bonded to the chlorine atom. So this is an alkyl halide. So of course it's going to react with sodium iodide, and sodium iodide is the source of the iodide ions, which are going to react as a nucleophile to displace the chloride ions, so that in the synthesis of allyl iodide. And in the second step, in the second example, this is also still a primary alkyl halide or alkyl chloride. And primary alkyl chloride or alkyl halides usually react through the SN2 mechanism, as we've seen in earlier lectures. So this reacts with potassium fluoride, the source of the fluoride ions, which are the nucleophile in this case, which will donate electrons towards forming a new bond to the electrophilic carbon and displacing the chloride ion as the leaving group. And the chloride ion will be stabilized by potassium to form potassium chloride. And the final product here, or the major product here, is ethyl fluoride. And also you have 18 crown 6. These are the this is one of the this is the reagent which is going to stabilize the potassium ions, as you'll see later how that happens and why it should happen. And also this is a solvent which is polar aprotic. So next time we are going to discuss on the factors that affect SN2 reactions, and we'll start with the effects of the nucleophile. Thank you.